All right, in the previous video we talked about apparent weight and what happens when you ascend upwards in an elevator. Now we'll do the opposite case. We'll descend downwards. So we're going to start at the very top of the building. We're at rest up here, and if we want to get going, our elevator is going to have to accelerate downwards. So let's give it an acceleration of negative 1.0 meters per second squared. Again, we'll still make the person, let's say the mass of the person's 50 kilograms here. And then throughout the majority of this is where you move at constant velocity. The elevator coasts downwards. And then what it has to do is it has to stop. So it's going to stop at the bottom. And in order to stop, what it has to do is it has to slow down. Since our velocity is downwards, we need an acceleration that's upwards here. So we're going to have a plus 1.0 meters per second squared for our acceleration. And if you think about it, this is typically where my knees would buckle, is at the bottom. So this is going to be interesting, because what ends up happening is a lot of people kind of go, okay, well, if you're going up, you feel lighter. But that's not what ended up happening in the previous scenarios. It was only here where we felt, or I actually misspoke there. A lot of people say when we go up, we feel heavier, because this is the first example we do. But what we find is that we don't feel heavier here, and we're still moving up. So we get everything happening here. We're actually going to feel lighter here, we're going to feel heavier here, and we're going to feel normal in these two spots. So the person still has the same two forces acting on them, the normal force and the force of gravity. So when we're looking at this, our expression is always something like this. Second law, and our two forces are normal force and gravity. Normal force is up, gravity is down. So again, if the acceleration is 0, you get the normal force equaling 490.5, which is our force of gravity as well. So we feel regular here. We feel normal. Once we get to the fact that an elevator starts moving, think about it. The floor is literally starts to move down. So what ends up happening is that we're going to feel a little bit lighter. In fact, what we do is we have a little bit less contact with the ground than we normally do. That's what the normal force entails. So our mass here is 50, our acceleration is -1, normal force is unknown, gravity is 490.5 newtons, and when we're accelerating downwards, now we're speeding up, what we get is that the normal force is equal to 440.5 newtons. So we feel lighter when the elevator begins to move here. And then as we descend in a constant velocity, our acceleration is 0. So what's going to end up happening is that when you solve for the normal force in this scenario, you're going to get 490.5 newtons again, just like we did in the previous one. So you feel normal here, you feel normal here. But let's look at this one, because this is one where people tend to get confused. We're moving downwards here, but our acceleration's upwards. This is going to cause us to slow to a stop. So we have sigma f equals ma, n is up, f g is down. A is now positive 1, and when you solve for n here, you get 540.5 newtons. So essentially, we feel heavier during this particular event here. So there is one point at which you can feel lighter, one point at which you can feel heavier. And it's got nothing to do with the direction that you're moving in, but everything to do with the direction of your acceleration. Keep in mind, your velocity is the direction you're moving in. The acceleration determines whether you speed up or slow down, and that is determined relative to the velocity. So we can do all types of things here. We can feel heavier, we can feel lighter. And turns out that, in all these cases, I gave you an acceleration of 1. But if this were a larger value, what's going to end up happening is it's going to affect n more. In fact, let's say if it really slowed to a stop a lot more rapidly than something like this value right here, you would get a much larger value of n, so you feel even heavier. So this effect is, let's say, increased with a larger acceleration. And the same thing here. If you actually, if your elevator got up to speed a lot faster here, you would feel even lighter because your A value would be larger and it'd be affecting your normal force even more. So there's actually a limit to how fast we can accelerate down, because what we want to do is think about our elevator here. Elevators are typically attached to a cable, and this is us. We're standing on a scale, and we're in the elevator. But what's going to happen is we're going to take a look at what happens when the cable snaps. Basically, we're in free fall now. And there's some amusement park rides that simulate this very well. I think the one that would come to my mind from Six Flags would be Zoomanjaro. They're dropping you from rest from an elevated position. If you go to Disney, I believe the Twilight Zone Tower of Terror does the same thing, although it's not quite as high as Zoomanjaro. But what this person is now in a chamber where it's falling down, so the acceleration is equal to negative g. And what will end up happening is that the reading on the scale is going to be nothing, because the person begins to float in the elevator as they fall down. What this is going to do is this is going to simulate zero gravity. Now if you think about our person here, there's a normal force acting on them, there's gravity acting on them. But once they cut the cord, let's take a look at this problem now. So we're going to set it up the exact same way that we would all those other problems. Here's the expression that we're working with. But now, let's actually write f of g as mg. And then let's also write, since a is negative g, let's write this out. The acceleration is m times negative g. We have n minus mg over here. If we add mg to both sides, you get a normal force of 0. Basically, what this is doing is this is changing your apparent weight to 0. This simulates us feeling weightless. So this is how you can simulate a zero gravity environment. In fact, I think one of the popular things that people used to do on these free fall rides all the time was they would put a penny on their lap and they would kind of watch the penny float in front of their eyes. It would look like you were at zero gravity. So this is how you can simulate a zero gravity environment, because what it does is it makes it seem as though your normal force is 0 acting on you and you're floating within a chamber here. They actually do something similar to simulate zero gravity for astronauts. So what they'll do is they'll put them in a plane, and in that plane what they do is they get up to a very, very high speed, right? And then in order to simulate zero gravity, what they'll do is they'll turn off the engine. And what that makes the plane is it turns the plane into an angled projectile, and the plane's going to do this. And, they can actually accomplish this for quite a long time. Now think about a projectile. The entire time the plane's a projectile, the acceleration is just negative g. It's straight down. So they've actually accomplished it a different way, but you could technically accomplish it by, if we were able to put you in a chamber and just fire you up with a velocity v and have you go straight up and straight down, that would also simulate it the entire time. So they do it in the plane, and then eventually in the plane they'll turn the engine back on, let's say right about there, because you don't want to fall forever. And so you're going to see that the acceleration due to gravity, having it be negative g, creates the zero gravity environment. So every time you watch them simulate zero gravity for some sort of training exercise, you're going to see them do it in the cabin of an airplane. And what I'll actually do is I'll link to a music video of a group that filmed their music video at zero gravity, and you'll see that at sometimes you'll be able to actually determine when they actually turn the engine on so that they're no longer a projectile, because you'll see the gravity suddenly kind of reappear. So it's a very interesting set of circumstances that we can do to simulate weightlessness.